When organizations ask me how to build a home STEM lab, they're hoping for a shopping list. What they actually need? A complete integration strategy. I'm Rajiv Patel, and I've spent years testing STEM curricula with real families and real kids. Today, I'm walking you through the phased implementation framework that turns scattered equipment into a functioning skill-building system. You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear is researched, written, and verified by real humans, but the voice you're hearing is AI generated. I want to be upfront about that. If you've been listening for a while, thank you. Seriously. It's great to have you back. And if this is your first episode, welcome aboard. We release new episodes every Monday, Wednesday, and Friday, covering practical STEM education topics for parents, educators, and anyone building learning environments at home. Let's jump into today's topic. Let's start with what we're actually talking about here. A home STEM lab isn't a toy collection or a hobby corner. It's a dedicated or adaptable physical space with hardware, software, and materials designed to enable progressive hands-on skill acquisition across science, technology, engineering, and mathematics. The defining characteristic? Every single component serves a specific position in what we call a skills dependency graph. That's the technical term for understanding which competencies must come before others. Functional labs run on three architectural principles. First, hardware compatibility layering. Your early-stage manipulatives have to bridge to screen-based programming environments, which then need to support migration to professional IDEs. Second, infrastructure adequacy. Power delivery, workspace ergonomics, ventilation, storage, all of it has to accommodate not just what you're using today, but 18 to 24 months of capability expansion. Third, curriculum alignment. Equipment purchases map to concrete, measurable milestones. Things like understands conditional logic or debugs Python syntax errors independently, not vague age ranges. The 2024 IEEE Spectrum Salary Survey confirmed what hiring managers already knew. Entry-level engineering roles now assume baseline proficiency in CAD software, version control systems, and at least one hardware prototyping platform. A properly architected home lab delivers these exact competencies, provided you build it as a system, not a wish list. Now, understanding how to build a home STEM lab effectively requires viewing it as a four-layer stack, where each layer depends on the one beneath it. Systems fail when parents optimize individual layers without considering integration points. Let's talk about layer 1, your physical infrastructure. This is the foundation. Power delivery determines what you can operate simultaneously. Minimum viable setup? 2 dedicated 15-amp circuits with surge protection rated for your equipment value. Most families drastically underestimate cumulative draw. A 3D printer pulls 8 to 12 amps during heating cycles, a desktop computer pulls 3 to 5 amps, an oscilloscope 2 to 3 amps, LED task lighting 1 to 2 amps. Run these on a single circuit and you'll trip breakers mid-print or mid-upload, and that teaches children that tools are unreliable when the actual failure is infrastructure planning. Workspace surface area has to accommodate concurrent projects. Entry-level minimum is 72 square feet of dedicated bench space. Think a 6-foot table plus a 4-foot auxiliary surface. This allows one active build, one documentation station, and tool staging. Insufficient space forces teardown between sessions, which destroys project continuity and discourages iteration. Environmental controls matter more than most guides acknowledge. 3D printing requires 18 to 26 degrees Celsius ambient temperature and less than 60% relative humidity for consistent layer adhesion. Soldering demands adequate ventilation, minimum 40 CFM exhaust for a small workspace, which typically requires a dedicated fume extractor unit, not just an open window. Ignoring this creates legitimate health risks and forces abandonment of entire skill domains. Storage architecture separates consumables like filament, components, and fasteners from tools and active projects. Climate-controlled storage for electronics components and filament means sealed containers with desiccant, keeping humidity below 40%. This prevents degradation. Tool organization using shadow boards or labeled bins reduces setup time from 15 minutes to 90 seconds. That's a 10-fold improvement in session initiation friction. Moving to Layer 2, your hardware platforms. This is capability enablement. Hardware selection follows a capability dependency model, not an age-indexed catalog approach. Each platform must expose progressively lower levels of abstraction while maintaining backward compatibility with prior learning. Unplugged coding foundations, typically ages 4 to 7, establish sequencing, conditionals, loops, and debugging through physical manipulatives. Products like Cubeto Playset or Code & Go Robot Mouse Activity Set build these fundamentals without screen dependency. Check the link below to see the current price. Critical specification here is the transition path to screen-based environments. Platforms that teach proprietary logic systems create what I call skill transfer debt. Children have to unlearn and relearn when moving to standard programming constructs. Visual programming environments, ages 7 to 10, introduce software-hardware integration. Scratch 3.0 and Blockly support extensions for robotics platforms and microcontrollers. Preferred hardware includes LEGO Education's Spike Prime set, which connects directly to Scratch via Bluetooth, no proprietary app required. Or the MakeBlock MBot Neo, which supports both Scratch and Arduino IDE, enabling later migration. Check the link below to see the current price. Lab requirement here: devices must be OS agnostic, meaning Windows, Mac OS, Chrome OS support, and they need to function fully offline after initial setup. Cloud-dependent platforms fail during internet outages and create vendor lock-in risk. Text-based programming and electronics, ages 10 to 14, demand Arduino-compatible hardware for a legitimate reason. Arduino IDE is the de facto standard in educational robotics, makerspaces, and prototyping labs worldwide. Learning Arduino C++ in middle school creates direct pathways to embedded systems coursework and internships. Recommended platform is the Arduino Starter Kit, which includes a comprehensive project guide paired with a breadboard component kit. Check the link below to see the current price. Power requirement: USB power delivery sufficient for multiple simultaneous device connections. Most laptops provide 0.5 to 1.5 amps per port. Projects requiring more than 1 amp need external 5-volt power supplies rated at 3 amps minimum. CAD and 3D printing, ages 11 and up, bridge digital design to physical fabrication. Software progression goes Tinkercad, which is browser-based and beginner-friendly, to Fusion 360, which is industry-standard parametric CAD with a free educational license, to Blender for mesh modeling with complex geometries. Hardware requirement is an FDM printer with PLA-only printing capability. No heated bed required for beginner use, which eliminates burn risks. You want a fully enclosed print chamber to reduce particulate exposure. Lab specs: dedicated 15-amp circuit, 4 or more square feet of non-flammable surface area, and ventilation delivering 4 or more air changes per hour. Layer 3 is your software ecosystems. This is skill scaffolding. Software choices must prioritize portability to professional environments over short-term engagement metrics. Programming languages follow a clear hierarchy: Scratch for visual learning, ages 7 to 10. Python for text-based, ages 10 and up. C++ for compiled languages, ages 13 and up for robotics and Arduino work. The Scratch to Python transition is well documented. The Python to C++ jump requires structured support. Development environments must support industry workflows. Python learners should use Jupyter notebooks, which support inline documentation and visualization and mirror data science workflows, or VS Code, which is the most widely deployed code editor in professional settings according to Stack Overflow's 2025 survey. Arduino learners graduate to Platform I/O, a professional-grade Arduino IDE alternative with superior library management, around age 14 to 15. Version control literacy starts at age 12 to 13 with Git and GitHub. This isn't optional. Every technical internship and entry-level role assumes Git proficiency. Installing Git locally and practicing commit, branch, merge workflows on personal projects delivers more career value than another robot kit. Layer 4 is curriculum sequencing. This is skill dependency management. The most sophisticated lab fails without structured progression. Curriculum architecture requires explicit prerequisite mapping. Milestone-based advancement replaces age-based recommendations. Here's an example sequence for robotics. First, demonstrates directional movement coding with visual blocks. Second, implements sensor-triggered conditional behavior. Third, debugs multi-step autonomous navigation. Fourth, writes Arduino C++ to replicate block-based programs. Fifth, designs custom sensor integration using datasheets. Each milestone includes a validation project, not a tutorial follow-along, but an open-ended challenge requiring independent application of the skill. Documentation requirements mirror professional practice. Starting at age 10 to 11, every project generates written documentation, problem statement, design approach, implementation notes, debugging log, and outcome assessment. This isn't busy work. It's training in technical communication, the skill that differentiates promotable engineers from code monkeys. Project complexity progression follows a 60-30-10 model I developed testing curricula with my own children. 60% of projects require recently learned skills for consolidation. 30% combine multiple prior competencies for integration. 10% require self-directed research and skill acquisition as a stretch. This distribution prevents both boredom from too much repetition and learned helplessness from too many consecutive failures. So, why does this matter? The economic case for building a home STEM lab properly centers on displaced tuition costs and accelerated credential acquisition. Here's the comparative cost analysis. A well-equipped home lab runs $3,000 to $5,000 in initial investment, then $500 to $800 annually in consumables and equipment upgrades. Weekly coding classes cost $150 to $250 per month, which is $1,800 to $3,000 annually. Robotics camps run $400 to $800 per week. Private STEM tutoring bills $75 to $150 per hour. A functional home lab delivers 10 to 15 hours weekly of hands-on practice time, which is impossible to match through scheduled classes at 60 to 75% lower cost over a 4-year middle school period. Credentialing acceleration is significant. Students with consistent home lab access complete AP Computer Science A coursework 18 to 24 months earlier than classroom-only peers, based on progression data I've tracked across more than 40 families. Earlier AP completion enables dual enrollment community college courses in data structures, embedded systems, or CAD. Those are credentials that directly reduce undergraduate tuition costs, $1,500 to $3,000 per avoided course, and improve internship competitiveness.
Hiring market alignment matters too. The 2025 IEEE workforce analysis identified persistent gaps in practical prototyping skills. Recent graduates demonstrate strong theoretical knowledge but require 6 to 12 months of on-the-job training to achieve basic proficiency with oscilloscopes, 3D printers, or soldering. Students entering undergraduate programs with these competencies secure research positions and paid internships 2 to 3 years earlier, compounding career trajectory advantages. The counterfactual matters here. Without structured home lab access, students learn these skills, if at all, during undergraduate years, using equipment they don't own, on schedules they don't control, in competitive environments where tool access is rationed. Home labs provide proprietary practice time, the 100 to 200 hours of low-stakes experimentation that separate competent practitioners from tutorial-dependent beginners. Now let's talk about types and variations. Physical space constraints and budget realities demand configuration flexibility. There are three proven models. Dedicated lab rooms, 100 to 150 square feet minimum, provide optimal functionality. Permanent tool mounting, project-in-progress storage without teardown, and environmental control independence from living spaces. This configuration suits families with unused bedrooms, basement areas, or garage space. Multi-purpose conversions adapt dining rooms, home offices, or bedroom corners using modular workbenches with folding legs and lockable casters, plus rolling tool storage. Setup time adds 3 to 5 minutes per session. Breakdown takes 2 to 3 minutes. This works for families accepting that trade-off. Critical requirement: dedicated storage that doesn't require moving lab equipment to access household items. Nothing kills project momentum faster than needing to dig through STEM supplies to reach board games. Staged expansion models start minimal: single workbench, screen-free coding kits, basic hand tools. Then you add capability layers quarterly based on milestone achievement. Initial investment runs $800 to $1,200. This approach matches expenditure to demonstrated engagement, but requires disciplined capability road mapping. You need to know which equipment to add next and in what sequence. All three models demand the same infrastructure fundamentals: adequate power delivery, temperature control, and ventilation. Skimping on infrastructure to afford fancier equipment is the most common and most expensive implementation error families make. Let's address some frequently asked questions.
What's the minimum viable investment to build a functional home STEM lab? Entry-level functional labs require $1,200 to $1,800 in initial expenditure. That breaks down to $400 to $600 for a proper workbench with storage, $200 to $300 for screen-free coding manipulatives, $150 to $200 for a used laptop or Chromebook meeting minimum specs, 4 GB RAM, 64 GB storage, $150 to $250 for a visual programming robotics platform with Arduino compatibility, $100 to $150 for basic hand tools and safety equipment, and $200 to $300 for infrastructure improvements, including surge protection, task lighting, and ventilation setup. This baseline enables progression from unplugged coding through visual programming with hardware integration, covering ages 5 to 11 skill development. Higher-tier capabilities, including text-based programming, 3D printing, and electronics prototyping, add $1,800 to $3,200 in subsequent phases. Equipment acquisition follows demonstrated milestone achievement rather than age or grade level. Establish a capability ladder. Screen-free coding manipulatives remain useful until the child completes more than 10 independent sequential logic challenges and demonstrates debugging by identifying the specific instruction causing failure. Visual programming platforms with robotics hardware enter when the child requests more complex behavioral control than manipulative support. Text-based programming tools deploy after the child successfully completes 15 to 20 Scratch projects, including variables, conditionals, loops, and custom functions. 3D printing equipment waits until the child demonstrates CAD proficiency by designing more than 5 functional objects in Tinkercad with dimension constraints. This approach prevents the common failure mode where equipment arrives before prerequisite skills exist, leading to frustration and abandonment. What technical specifications should you prioritize when selecting a computer for the home STEM lab? The computing platform must support simultaneous operation of Arduino IDE or VS Code, Chrome browser with more than 10 tabs for documentation, Fusion 360 or Tinkercad, and 3D printer slicing software without performance degradation. Minimum specifications as of 2026: 8 GB RAM, though 16 GB is strongly preferred for CAD work. 256 GB SSD storage, not HDD. Compile times and software launch speeds directly impact frustration tolerance. Intel i5 or AMD Ryzen 5 processor or better, and USB-A ports supporting 1.5 amp delivery for Arduino and robotics hardware. Operating system selection depends on software ecosystem. Windows supports all STEM platforms and games. Mac OS handles programming and CAD well, but excludes some robotics software. Chrome OS works for Scratch and Tinkercad, but fails for Arduino IDE and Professional CAD. Budget allocation: $500 to $700 for a refurbished business-class laptop meeting these specs delivers better value than $400 new consumer models with inadequate RAM and processors. What safety certifications and lab infrastructure do you need before introducing soldering and 3D printing? Soldering requires fume extraction, delivering minimum 40 CFM at the work surface, a silicone work mat rated to 260 degrees Celsius, a soldering iron with temperature control and safety stand, and safety glasses meeting ANSI Z87.1 impact standards. Children under 12 work under direct supervision. Ages 12 to 14 work independently after demonstrating proper iron handling, tip cleaning, and solder application across more than 20 supervised joints. 3D printing demands fully enclosed print chambers for particulate containment, PLA-only filament use, ABS and PETG emit concerning volatiles, a dedicated 15-amp circuit, and a non-flammable surface base. Fire safety includes a rated ABC extinguisher within 10 feet of printing and soldering stations, working smoke detectors with 10-year sealed batteries, and adult verification of proper equipment shutdown. These aren't optional, they're the minimum standards for responsible skill development. Here's the summary. Learning how to build a home STEM lab effectively requires rejecting the consumer mindset that equates spending with capability development. The functional lab operates as an integrated system. Physical infrastructure enables hardware operation, hardware platforms expose progressive skill layers, software ecosystems bridge to professional tools, and curriculum sequencing ensures each capability builds on validated prerequisites. The families who succeed treat lab development as multi-year infrastructure investment. They plan power delivery before buying printers, establish storage architecture before accumulating components, and map curriculum progressions before ordering robotics kits. The families who fail accumulate impressive-looking equipment that never integrates into coherent skill development. Your implementation checklist: audit existing space for power and ventilation adequacy, establish baseline equipment supporting current skill level, document the next 3 capability milestones with validation criteria, identify prerequisite hardware and software for each milestone, and schedule quarterly reassessment of progression pace. Start building systems, not collections. That wraps up this episode of the STEM Lab podcast. Thanks for listening. We've got new episodes coming out every Monday, Wednesday, and Friday. If you found this one useful, I'd really appreciate it if you could leave us a 5-star rating and write a quick review. It genuinely helps other people discover the show when they're searching for STEM education resources. And go ahead and hit subscribe or follow so you get notified the second a new episode drops. I'll catch you next time.